4.8 Attractive Forces in Compounds, or the answer to your question that you've always wondered, why is a snowflake the shape it is? Well, it has to do with the attractive forces between those water molecules when they freeze. And all of this has to deal with the attractive forces in compounds. And when we're talking about this, we're talking about the attractive forces between compounds. That's what this section is all about. So this is an example of a water molecule here, another water molecule here. Why in the world would there be this attraction to keep these two molecules together? Well, let's look up here at the charges and maybe you can figure that out. But if not, we'll soon learn. Well, when you're talking about covalent compounds, we learned in our last section that we had covered how to determine that a covalent compound was either polar or nonpolar. And so if a molecule was polar, and we determined that by looking at the electronegative value chart and subtracting, and if it was 0.5 or greater, it was determined to be polar, which means we said it act charged. So, in covalent compounds, polar molecules exert attractive forces called dipole-dipole attractions. Notice how similar the word dipole is to polar. Well, if a molecule is polar, it will have the dipole-dipole attractions. This is important because the side that's negative will form intermolecular bonds with something positive on the other molecule. And the side that's positive will form intermolecular bonds with something that's negative on the other molecule. And that is an attraction between molecules. Now, if it's a really strong attraction, this happens when we have hydrogen that's attached to fluorine or oxygen or nitrogen. Those are very electronegative atoms. And this particular dipole attraction is so strong and it's so special that it has its own special name called hydrogen bonds or hydrogen bonding. Please do not think that hydrogen bonds mean when hydrogen is attached to anything. No. It refers to when there's this attraction between hydrogen and fluorine, or hydrogen and oxygen, or hydrogen and nitrogen. Hydrogen bonds are very important in why water has the attraction it does, as in that snowflake. Because of the very polar, the very strong hydrogen bonding to other molecules, it's not only important in making snowflakes, but it's also very important in lots of our biological processes because of how much water makes up the cells in our body. And remember, hydrogen bonding occurs only with hydrogen and oxygen, or hydrogen and nitrogen, or hydrogen and fluorine between the molecules. So hydrogen bonding is the strongest force between covalent molecules and plays a major role in the shape of DNA. So let's look here. Remember, our hydrogen is going to be partially positive because the electron is going to be spending more time around the oxygen, or partially negative. So, because it's partially positive, not only is it bonded to the oxygen in this of its own water molecule, but there is an attraction to an oxygen of another water molecule. Why? Because it's negative. Positive and negatives are going to have this attraction. Here's another example. The hydrogen attached to our fluoride ion here is going to be more partially negative because it's going to be holding the ions a little bit closer, the electrons a little bit closer, and so when it does, it's going to be partially negative, and then this hydrogen of this other molecule is going to be partially positive. There will be this attraction here, and this attraction is what's called the hydrogen bond. Now, if we don't have polar molecules, then it's not that there is no attraction between different molecules. It's just that the attraction is much weaker. So quite often, if it's a smaller molecule, if something only has dispersion forces, then it's probably going to not have enough attractive forces to make it be a liquid at room temperature, and so the smaller molecules will be gases at room temperature. So what is a dispersion force? Well, sometimes other books also call it London dispersion forces, but it really is based on the number of electrons in the molecule. So the more electrons, the more dispersion forces there are. And so when the molecules are kind of moving around, if they bump into each other, then they can kind of force some of the electrons to move to the other side, causing this temporary dipole, this temporarily partial charge, and so there is a little bit of attractive forces there. Now, the example that's given is a perfect example because you might have you might have gas or you might have gasoline. So let's say you have natural gas at your house. It's a gas. Well, why? Because it is going to be our methane, and it has a total of let's see, how many electrons does carbon have? It's going to have 6. Hydrogen has 1, but we have 4 of them. So it has 10 electrons, 10 dispersion forces. That's not enough to connect with another methane molecule to make it be a liquid. And so it is a gas at room temperature. Whereas even though this particular C7H16 heptane has only the dispersion forces, because it's not an ionic bond, it's not polar, it's not hydrogen bonding. But by this time, if you count up how many electrons there are in this molecule, 58, this is a liquid, and this is one of the components of the gasoline you pour into your car to make your car go, okay? But you know that it has to be big enough, if it only has dispersion forces, for it to be a liquid at room temperature. So as we look at this chart, if it's an ionic bond, we don't have to wait around for any partial charges to happen. Electrons are transferred. So there is this charge, this ion, these ions that are held together. Very strong arrangement. Sodium chloride is an example. At room temperature, anything with ionic bonds is going to be a solid at room temperature. Covalent bonding can have a different variety of types of attractions depending on the strength of our partial charges here. The strongest one we mentioned was a hydrogen bond. When hydrogen is attached to fluorine, oxygen, or nitrogen, not as strong, but better than dispersion forces is the dipole-dipole attraction. So you'll see there's a little bit of attraction here between this molecule and this molecule. And the weakest one of all, we mentioned, were the dispersion forces that only had to do with the amount of electrons. And at room temperature are quite often gases, unless they're big enough to have enough electrons to make a difference. So, melting points and attractive forces, what we've alluded to on our last slide. Melting points of compounds are related to the strength of attractive forces between molecules or compounds. They are lower due to weak forces such as dispersion forces. They are higher with stronger attractive forces, and even higher with hydrogen bonding because it has such strong attractive forces. They are usually liquids at room temperature, with exceptions. But the highest of all are ionic compounds, due to the very strong attractive forces between ions in the compound. So they are going to be, at room temperature, they're going to be solids. So when we look at this next table, at the melting points, you can definitely see the difference in melting points of ionic compounds compared to the items that exhibit hydrogen bonding, compared to those with dipole attractions, compared to those with just our dispersion forces. Now remember, when you are asked to determine what type of attractive forces something will have, you are going to need to look at your electronegative chart to determine if there's going to be a dipole-dipole. So, identify the main type of attractive forces that are present in the liquids of the following compounds. Are they ionic bonds, hydrogen bonds, dipole-dipole, or dispersion forces? Press pause and come back with your answer. All right. You are back with your answer. If you look, hopefully you got these. Let's first of all look to see why NF3 is what it is. First of all, it's not an ionic bond because the first one's not a metal. Then we know the next strongest is our hydrogen bonding, it's not that because there's no hydrogen. So then we check the dipole-dipole. We check to see if this is going to be polar. Well, nitrogen's value is 3.0 on our electronegative chart, and fluorine's value is 4.0. So yeah, that difference is 1. So consequently, that's going to form a polar molecule, so that is going to be a dipole-dipole force. Water, by now, we've already mentioned it's hydrogen bonding. It's not an ionic bond, and there's hydrogen bonding in it because there's an oxygen to hydrogen, and it will bond with another water molecule, form attractive force called hydrogen bonding. C, Br to Br. Well, I don't care what electronegative value Br has, it's hooked up with another Br. So whatever the value it is, minus the same value, is an overall 0 value for electronegative value. And so consequently, it can't have any dipole-dipole of any sort. There's no hydrogen around for hydrogen bonding at all, plus it's not the right atom. The only thing it does have is dispersion forces. Okay, KCl. Well, the first one's a metal, so we know it's an ionic bond. NH3. Well, we have hydrogen and that it's attached to a nitrogen. Right then and there, we know it's hydrogen bonds. We have HBr. It is not an ionic compound. It is not hydrogen bonding. Why? Because hydrogen is not bonded to oxygen, nitrogen, or fluorine. So then we check the electronegative values. So hydrogen we know is 2.1. Our bromium is 2.8. We subtract that, that's 0.7. That means it is a polar molecule, hence dipole-dipole forces.